my KCET 2026 aspirants, welcome back to Sankalp series. And in today's class, we are going to discover whether Dr. Soumik sir were able to prepare the antidote in time or not, or whether we were able to save JJ ma'am or not, right? So, or if we saved, how was it done? How much time did we take? So, everything we'll be talking about, and what decides how much time, how much product, rate of the reaction, how it is decided, and also we'll be talking about what is the effect of temperature on the rate of the reaction. Okay, going to be very important lecture, so please watch till the end and also solve the questions with me. Okay, so coming to the part 2 of this one, so today we have integrated rate equation and the dependency of the temperature. Okay, now coming to integrated rate equation, so here Soumik sir is in deep thought in ICMR lab. Okay, he is thinking that I have taken right amount of concentration, right amount of catalyst and right amount of temperature, but still will I be able to prepare the antidote in 24 hours? Will be that enough? That how much antidote will be prepared? Will that much quantity be enough to save JJ ma'am or not, right? So these all answers, these all questions are being answered by something called as integrated rate equations. Okay, what does this integrated rate equations tells us? It tells us that how the reactant concentration changes with time. Means suppose you have started with 1 molar. After 60 minutes, what will be the concentration of the reactants? After 40 minutes, what will be the concentration of the reactants? So how the reactants concentration change with time? That's the first thing. Second, predict how much product will be formed after t minutes. Suppose you have passed 20 minutes, after that how much product is formed, how much reactant is consumed. So these all calculations comes with integrated rate equations. And next, decide if we will make the antidote before 24-hour deadline or not. So that is according to the story that we have, right? So what does integrated reaction tells us? Integrated rate equation, tells us that whether how much time, after how much time, how much concentration of the reactant will change. Okay, so we will be studying integrated rate equations for the 3 different orders. So actually it means, I can say briefly, it gives the relation between the time and the concentration of the reactants. Okay, this is very important. 2 things, relation between time and the concentration of reactants. Now we will be studying integrated rate equation for 3 orders: 0th order reaction, 1st order reaction, and what is pseudo 1st order reaction. These 3 reactions we will consider, and we will derive the integrated rate equation for each order. Okay, so the first order that we have is 0th order, and in this, if I tell you, according to rate law, I can say that rate is independent of the concentration. Okay, rate is independent of concentration. That's the first thing. And how do we write that? So we have, let us derive the equation now. Okay, so for example, you have a reaction R gives P. Okay, now according to rate law, I can say that rate is equal to or I can write rate is proportional to R to the power of n. Okay, where n is equal to 0 because this is a 0th order reaction. So I can say that rate is proportional to R to the power of 0, that is 1. Okay, or to remove this proportionality, I can say rate is equal to K. This is equation number 1. Clear? Now we have another thing, rate is equal to minus dr by dt. This is also equal to rate according to the differential rate law equation. So this is equation 2. Now if I equate both of them, I can say that K is equal to minus dr by dt. Then what will be equal to this one? Minus dr is equal to K dt. Now let's take the integration on both the sides. Now this will give me minus r is equal to KT. Okay, now when I take integration, and when you complete the integration, we get an integration constant. So here I is the integration constant. Now what I want to do, I want to find the value of this I. So what I can do is, you have to consider that let time is equal to 0. Okay, let me see when you have started the reaction. So when the reaction is started, what will be the concentration of the reactant? It will be equal to R0, where R0 represents what? Initial concentration. right? So I can write here minus R naught is equal to K into 0, that is I. So what's the value of I here? Minus R naught. Now what I will do, I will substitute this one in the given equation. So I have got this one, minus R is equal to KT plus what is I value? Minus R naught. Okay, I'll just write it like this. Yeah. Okay, now I can just arrange this. R naught minus R is equal to KT. Okay, R naught minus R is equal to KT. Now what all things we have? R naught is the initial concentration, R is equal to final concentration, okay, K is equal to rate constant, T is equal to time. Okay, so this is my equation. This you have to remember. R naught minus R is equal to KT is the integrated rate equation for the first order reaction. Okay, now moving towards the next thing, that is a graph for this one. So if you want to see the graph, we have this one, right? R naught minus R is equal to KT. Now I want to draw a graph for R versus T. Okay, so this has to be my y-axis, this has to be my x-axis. So can I just arrange it? So I will write the equation like this. R is equal to minus KT plus R naught. Okay, this is my equation. Now here what you see, this is y, this is m, x plus c. So what is my slope of this equation? Slope of this equation is minus k. So you can see if I draw a graph for R versus T, you have this line which is having a negative slope, that is minus k, and you can see that the intercept here is something that is R naught. Okay, R naught is the intercept here. Clear? So that is how we will draw the graph for this one. And next I will give you some examples of zeroth order reactions. This is very important because question will be like, the example will be given, this is a which order reaction. So at least 2 to 3 examples from each order you should remember. So enzyme catalyzed reactions, decomposition of ammonia on a hot platinum surface, thermal decomposition of HI on gold surface. So these are the examples of zeroth order reaction. Okay, now we will go to something very important, that is half-life. So first of all you have to understand what is half-life. Half-life meaning, if I just talk about the definition of half-life, what is T half? Time required, okay, to complete half of the reactants. Time required to complete half of the reactant concentration. Time required to complete half of the reactant concentration. Okay, so now how can I solve this? We have this one, that is R naught minus R is equal to K into T. Okay, now at half-life means what is happening? This much means how much amount is already consumed? Half is already consumed. So what is this R here? R is the final concentration. So if half is already consumed, then half will be remaining. So for example, if you have started with 10 moles, okay, after T half you will be having 5 moles, right? Half of this one. So can I substitute here? If I take T equal to T half, then my R will be equal to half of initial concentration, right? R will be equal to half of initial concentration. Let us substitute this one here. R naught minus R naught by 2 is equal to K into T. Now you will get here R naught by 2 K. I can just write like this. This is T half, right? By 2K is equal to T half. So this is again a very important equations that you have to remember. So what is the T half for a zeroth order reaction? A naught by 2K, where R naught is what? R naught is your initial concentration. Okay, K is the rate constant. Clear? Now we will move to some quiz time where you will be solving questions based on the zeroth order reactions. Okay, so the first one here is a substance reacts with initial concentration of A moles per decimeter cube. So what is the initial concentration? Okay, A moles per decimeter cube. According to zeroth order kinetics, the time it takes for the completion of the reaction is, so time it takes for the completion of the reaction, you have A naught minus A is equal to K into T, right? So now here what I want to calculate, T here. What is the value of T here? The time required for the reaction is, okay, the time it takes for the completion of the reaction. Completion of the reaction means final concentration is 0. So what is this A value? A value will become 0. So I can put here A naught minus 0 is equal to K into T, or T is equal to A naught by K, where A by K is there. Okay, so what will be the answer here? That is option number C. Okay, A by K. Now we have question number 2 here. The reaction X plus W gives Y plus Z would be a zero order reaction when rate remains unchanged at any concentration of Y and Z. The rate of the reaction doubles if the concentration of Y is doubled. The rate of reaction remains same at any concentration of X and W. So first of all, the rate is not affected by the product concentration. It is affected by the reactant concentration. So here I can remove this option, here I can remove this option. Now since it is a zeroth order reaction, it doesn't depend on the concentration of the reactants. So the rate of the reactions remains same at any concentration of X and W is the correct answer. Okay. Moving to the third question here, the general reaction X to Y, the plot of concentration of X versus time in the given figure, what is the order of the reaction and what are the units of the rate constant? So just now we have seen the graph. For zeroth order we get this graph, so it has to be zeroth order. I can eliminate these options. Next, what is the unit of zeroth order? So if you remember, K formula was moles to the power 1 minus n, liter to the power of n minus 1 second inverse. Now I'll get mole liter second inverse. Okay, so that is mole liter inverse second inverse and zeroth order. So option number A here. Next we have question number 4. The above plot is for dash order reaction to calculate the value of the rate constant. So if you see, it is a zeroth order reaction. So the above plot is a zeroth order reaction to calculate the value of rate constant. Now moving to the fifth question, for a zeroth order reaction, the plot of concentration of product versus time is a straight line width. Okay, so if you see the concentration of product versus time, okay, so if you see, we have concentration of product, okay, is always a positive slope because product concentration increases. So we have a positive slope here, so I can eliminate these two options, and a zero intercept. Okay, so it has to be a positive slope, and the intercept, as you have seen, will not be 0. Okay, so it without a zero intercept, non-zero intercept. So the correct answer here will be option number C. Next we have first order reaction. The rate of the reaction is proportional to the first power of the concentration of reactant R. So similarly, how we have derived the rate equation, integrated rate equation for zeroth order, in the same way we will derive it for the first order as well. Okay, so this derivation is not required for KCET examination, but in PU board this is a must question, so you do have to prepare that. So let us see here. I have suppose the reaction R gives P. Okay, so what will be rate here? Rate will be proportional to R to the power of 1. Okay, then you have rate is equal to K into R. Okay, then you have rate is equal to minus dr by dt. Okay, this is equation 1, this is equation 2. Now if I equate both of them, I have Kr is equal to minus dr by dt. Okay, next we have K dt is equal to minus dr by r. Okay, now if I do integration on both the sides, Okay, if you integrate both the sides, you will get KT, okay, is equal to minus log R. Okay, so integration of 1 by R dr is log R. So not exactly log R, it comes as ln R. Okay, so I'll write it as ln R plus I. Okay, I is there. So how do we find the value of I? So you have to take t equal to 0, and at that time R is equal to R naught. Right? So then if I find out k into 0 is equal to minus ln of R naught plus I. So what is the value of I here? Ln of R naught. Right? So now we can substitute here KT is equal to minus ln of R plus ln of R naught, that is equal to ln of R naught by R is equal to k into t, kt equal to 2.303 log of R naught by R. Okay, so this we will get one thing. Now what I can do, see this can also be written like this, that e to the power of kt, okay, e to the power of kt is equal to R naught by R. Okay, you know just what I have done, I have taken anti-log on both sides. So if you take anti-log of both sides, this power will go up. Next what I can do here, I'll just write down here. So it can be written as I can write like this. Now if I take the reverse, R by R naught, okay, is equal to e to the power of minus kt, and finally R is equal to R naught into e to the power of minus kt. So this is also an important equation, okay, and we have this also as an important equation. For numericals, this equation will be mostly required, and for graph and all, this equation will be required. So now let us see the graph of this particular thing. So one second, yeah. So you have this graph. So if I tell you, the first thing that we have seen, the equation was kt is equal to ln of R naught minus ln of R. Okay, so now once I solve this, I'll get ln of R is equal to minus kt plus ln of R naught. Okay, so we have this y m x c. So you can see the y value is ln R. Okay, this is y value, x value is t, and you have minus k, the slope value is minus k, and the intercept here is ln R naught. We got this one. Then we have another graph we can do. We have also seen that kt is equal to 2.303 log of R naught by R. Okay, so if you solve this, so what I will get, if I have log R0, if I take this side, okay, y is equal to, I have an equation like this, I'll just erase this one, okay, log of R naught by R, right? So here if I have slope y equal to m into x, so x is time and this is k by 2.303. So the slope is a positive slope, k by 2.303, y is this one, that is mx, and this side we have time here. Okay, so that is a different graph now. So we have two types of graph. Now next we will see is the examples of first order. Okay, so you can see hydrogenation of ethene, natural and artificial radioactive decay, and decomposition of N2O5 and N2O. These are all examples of just a minute, yeah, so these are all examples of first order reactions. Okay, now let's see the half-life derivation. Okay, so what is our equation for first order? Kt is equal to 2.303 log of R naught by R, right? So if I solve this, what will happen? Kt equal to 2.303 log of R naught, okay, at T half, means when T is equal to T half, what will be the concentration of R? R is equal to R naught by 2, right? So it is R naught by 2. Now here I can write this as T half. So T half will be equal to 2.303 by K log of 2. Okay, now if I solve this, I will become 0.693 by K. Okay, T half is equal to 0.693 by K. Okay, this is the half-life equation. Next, we have now come to the ICMR research where Somik sir is still calculating using this integrated rate equation, and let's see what he has seen. So the preparation of antidote is going on, and the time left already in this discussions and all, already 4 hours has been gone, and we are just left with 20 hours now. Okay, so now the reaction has already started and the calculation is in progress. So let's see what has happened now. So if you see in the first case, okay, so I'll show you. In the first 5 hours, only 20% was prepared. 20% of the reactant was converted to the product, and so only 20% was there, and that was not enough to save JJ Mam. Then if you see after 10 hours, 60% is prepared. Okay, so it is still risky. We have to make it more. Okay, can we make it in time? So there's confusion that can we prepare it in time. Now when we reached 15 hours here, so we are almost done. 90% is done by 15 hours, and but yes, it is still not enough because we want 100% of the products to be consumed. So at 20 hours, what happened? We have got here victory. So within the time limit, all the required amount of antidote was produced, and we could have saved our, means we have saved our JJ Mam. Okay, so that is the story here that you should be knowing, that in a particular time how much it is important that to convert the reactions in a particular amount of time, how much product is formed. That calculation is so important, you would have understood by this particular example, right? So now we will move to some quiz time questions on the first order reactions. So what is the 2/3 of a first order reaction having K equal to 5.48 into 10 to the power of minus 14 second inverse? Okay, so you have to find the time, okay, the time required for 2/3 of a first order reaction to be completed. So now see, if I solve this, I'll get K equal to 2.303, okay, K equal to 2.303 by log of A naught by A, right? So if 2/3 of a first order reaction is completed, then how much is remaining? 1/3 is remaining. So what is this A value? The final value is 1/3 because 2/3 has reacted. So you will have 2.303. I'll put K here, this one. K value is 5.48 into 10 to the power of minus 14 into log of 3. Okay, so if I solve this, I'll get 2.01 into 10 to the power of 13. You can check the calculation, that will be the answer here. Okay, now moving to the next question. The decomposition of a substance follows first order kinetics. If its concentration is reduced to 1/8 of its initial value in 24 minutes, the rate constant is, so if you have seen rate constant formula is what? 2.303 by T, the log of A naught by A. Okay, so now what I have here, K equal to 2.303 divided by 24 log of A naught by A. So A naught is 1 and here we have 1/8. Okay, so reduced to 1/8 of its initial concentration, means final concentration is 1/8. So now 8 goes up, so you will have 2.303 divided by 24 log 8. Okay, so now if I solve this, you can calculate, or you don't have to solve it, you can see it in the options. So 2.30 by 24 log 8, so that is option number D here. Now moving to next question, that is question number 3. The rate constant in case of a first order reaction is inversely proportional, independent, directly proportional, inversely proportional. So directly proportional to concentration units, because we have this formula, rate is equal to K into A to the power of 1, right? So it is directly proportional. Now second is question number 4 here. The mathematical expression for T1/4, that is when 1/4 of the reaction is over following the first order kinetics, can be given by. So we have this T1/4 when 1/4 of the reaction is over, means 1/4 of the reaction is over. So how much is remaining? 3/4 is remaining. So I can write K equal to 2.303 by T1/4 log of 1/3/4. Okay, so it goes up. So T1/4 is 2.303 by K log of 4/3. That is option number C here. Now we have question number 5 here. The first order reaction was started with a decimolar solution of the reactant. Okay, 1 decimolar. After 8 minutes and 20 seconds, its concentration was found to be m/100. So the rate constant of the reaction is, so decimolar means 1/10 molar. Okay, this is decimolar. So let's solve this. We have K equal to 2.303. Okay, you can see the unit is second inverse. So if I convert this to 8 minutes and 20 seconds means it is 500 seconds. Okay, log of initial concentration is 1/10 and the final concentration is 1/100. Right, so this will cancel. So I will have this much, 2.303 by 500. How can I solve this? So you will get 2303 into 10 to the power of -3. Okay, yeah, divided by 500. So if you see 5 4s is 2000, so something I'll get near to that. So 4.606 into 10 to the power of -3 will be the correct answer here. Okay, so now we will go to the next thing, that is pseudo first order reaction. Now see, there was particular example I have taken during the hydrolysis of esters. Means you know esters are made up of alcohols and acids. So when you take an ester and add water and H+, it's get converted to acids and esters. Okay, so during the hydrolysis, so if I have taken 0.01 mole of ether and 10 moles of water, after the reaction you can see this will completely hydrolyzed and this has become from 10 molar to 9.99 molar. So practically speaking, if you see, there is no change in the concentration or negligible change in the concentration of water molecules, right? So that means what? Now that tells you that the amount of reactants and products at the beginning and the completion of the reaction are given as under. So now you can tell me that out of these two, this constant, though the reaction is affected by both both ester and water, but the concentration of water is not that much, or the effect or the change in the concentration of water is not that much prominent. So I can say that the reaction directly depends only on the concentration of the ethyl acetate. So the hydrolysis of ethyl acetate, which is a chemical reaction between the ethyl acetate and water, in reality it is a second order reaction. Okay, and the concentration of both the ethyl acetate and water affect the rate of the reaction, but water is taken in large excess for hydrolysis, right? Because you can see the concentration of water is too high. Therefore, the concentration of water is not altered much during the reaction. Okay, the concentration of water is not changed. So that is why the rate of the reaction is affected by the concentration of ethyl acetate only. Okay, though both are important, but this concentration change is negligible, so we can say that it depends on the ethyl acetate. So such type of reactions where the reaction is actually a second order but it becomes first order, or it is visible as first order due to the excess presence of concentration of any one of the reactants, such reactions are called as pseudo first order reactions. Okay, I hope this is visible. Pseudo first order reaction. There is one more example of pseudo first order reactions. Both of these are asked in the examination, so you should remember. Inversion of cane sugar is another example of pseudo first order reactions. Okay, cane sugar is converted to glucose and fructose. Okay, now we will talk about temperature dependency. So before that, we'll give you an example. This is a reaction. 2N2O5 gets converted to 4NO2 plus O2. Now see, we have discussed in the starting that there are three major factors which affect the rate of the reaction. The first one is concentration, second one is temperature, and third one is catalyst. So we have already discussed everything about concentration. Now we are moving towards the second factor, that is temperature. So if you see this reaction at 50 degrees Celsius, it took only 12 minutes. For 25 degrees Celsius it took 5 hours, and for 0 degrees Celsius it took 10 days to complete the reaction. So definitely when I can say that if temperature increases, the rate of the reaction will also increase. Okay, that is something we have understood here. Now what was observed? That for a chemical reaction with a rise in temperature by 10 degree, so if the temperature changes by 10 degree, the rate of the reaction is nearly doubled. Okay, so for every 10 degree there is a double in the rate of the reaction. Okay, so now we will talk about most in detail about Arrhenius equation. So like if the relation between the rate and concentration is given by the rate law expression, right? Similarly, the relation between the rate and the temperature is given by one special equation called as Arrhenius equation. K is equal to A into e to the power of minus EA by RT. Now what is K here? Rate constant. What is A here? Arrhenius factor, frequency factor or pre-exponential factor. EA is called as activation energy, R is called as gas constant, and T is called as temperature. Okay, so this is there here. This equation is important. Now what is next? I'll first discuss about the Arrhenius theory. What does Arrhenius theory tells us? Now see, Arrhenius theory says that whenever two molecules are reacting, okay, they do not form product directly. There is one intermediate state formed between that, and this intermediate is converted to product. Okay, so you can see according to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. This intermediate has to be formed. Okay, this intermediate is very unstable and it exists for a very short time and then breaks to form the two molecules of hydrogen and iodide. So you can see here what the reaction is saying, or what Arrhenius says, that if H2 and I2 is reacting, okay, first they will get converted to an activated complex, not directly product, and after this activated complex is formed, the energy will be released and you will get a product here. Now what is this? The energy required to convert the reactants to this activated complex is called as the activation energy. Okay, that is clear. So the energy required to form this intermediate called activated complex, this one is your activation energy. Okay, next I'll talk about something called as Boltzmann distribution. Okay, this is very important. So first let me give an idea of Boltzmann distribution. So now to understand the effect of temperature, we will talk about something called as Boltzmann distribution curve. Okay, so there were two scientists. Okay, so Boltzmann said that see, the distribution of the kinetic energy may be described by plotting the fraction of molecules with a kinetic energy E versus the kinetic energy. So there was a graph plotted down where we have this fraction of molecules, where fraction of molecules is equal to what? Ne divided by Nt, means total number of molecules, and here Ne stands for the number of particles having energy E. Okay, and the plot is versus kinetic energy. Okay, so now this graph is done here, and this point represents the most probable kinetic energy. Now what is this most probable kinetic energy? It is that point, or this is that value where, means the maximum number of particles, okay, maximum number of fraction of particles have this much energy, right? That is the most important thing that you should know. Most probable kinetic energy means the energy that is possessed by maximum number of particles. Next, the peak of the curve corresponds to most probable kinetic energy, that is the kinetic energy of maximum fraction of molecules, and there are decreasing number of molecules with energies higher or lower than this. Means if you consider energy higher than this, then also the fraction is decreasing. Energy lower than this, then also the fraction value will decrease. Okay. Next we will understand in the same curve what happens when the temperature increases. Okay, this is very important. Now when the temperature increases, the maximal Boltzmann curve shifts to higher energy and broadens. So if you see, this is at this is at temperature T, but at T plus 10 what happens? This was the point of most probable kinetic energy. Now this becomes the point of most probable kinetic energy, right? So the graph shifts towards the right, and also it becomes smaller and flatter. Okay, and the next thing is more molecules gain energy higher than the curve as the more molecules gain higher energies as the curve spreads to the right. So what does, when it shifts right, that means what? Number of particles having more energy is increasing. Okay, the curve is moving to this side, but the area under the curve remains constant. The total probability is the 1. So area will remain same. So if the width is increasing, the height is decreasing. The reason for that is the area should be same. At higher temperature, a greater number of fraction molecules have energy greater than or equal to EA. Now this is activation energy, right? So at temperature T, you have these many particles which was having energy greater than EA. Now as the temperature increase, you have more number of particles having energy greater than EA. Okay, so at higher temperature, so this increases the rate of the reaction. Fraction with energy greater than EA may doubling the rate of the reaction. So in the starting, we have discussed that as the temperature increases, right, as the temperature increases, the rate of the reaction will increase, right? But what is the reason behind it? The reason behind it is this one. When you increase the temperature, the number of particles having energy greater than the threshold energy or greater than the activation energy increases. So when the number of particles having energy greater than the activation energy increases, they will collide better and there's a high chances of getting product formation. So that is why the rate of the reaction also increases here. Okay, so now if we have seen the what I'll say, the graph, or I can say the Arrhenius equation. What is it? K equal to A into e to the power of minus EA by RT. Now taking ln on both sides, ln K is equal to ln of A minus EA by RT. Now if I draw a graph for this one, y is equal to, or I can just arrange it in the form of, one second, yeah, I can arrange in the form of ln K is equal to ln A minus EA by R into 1 by T, right? So this is Y, this is M, this is X, and this is C. So we have this equation here. So you can see here, if I just draw the graph of this one, what is my Y axis? Y axis is ln K, and what is X axis? 1 by T, and the slope is EA by R, and the coefficient, or I can say the intercept is equal to ln of A. Okay, so this is the graph here. Now what happens? See, what happens here is when you consider two different temperatures, we get an equation which we use in the question solving mostly, that is log of K2 by K1 is equal to EA by 2.303 R T2 minus T1 by T1 minus T2. So I'll just tell you how we have derived it. See, just now we have got ln K is equal to ln A minus EA by R T1. Let this be two equation. Then ln K2 means another rate at another temperature, that will be equal to ln A minus. Okay, so what I can do now, I can subtract these two equations. Okay, so if I subtract, I'll get ln K1 minus ln K2 is equal to ln A minus ln A. Okay, then you have minus EA by RT1, okay, and minus of minus, this one will become plus EA by RT2. Now what I can do, this one I can write ln of K1 by K2 is equal to minus EA by R 1 by T2 minus 1 by T1. Okay, now what I can do, I can take this subtraction, this minus side on this side. So if I take this, I'll get ln of K2 minus K1, okay, is equal to, one second, we are subtracting this minus this, right? Yeah, so here I have taken minus common. Okay, so it will become minus 1 by T2 and plus 1 by T1, right? So I have taken minus here common. So what I will get, this if I just arrange it, EA by R into 1 by, so you have 1 by T1, so T2 minus T1 by T1 into T2. Now to convert this ln to log, you can multiply this 2.303. So you will get this as the final equation. So when we have two rate constants at two different temperatures, we can calculate this way. Okay, so let's solve some questions from this point. So for every 10 degree rise in the temperature, the rate of the reaction, we have discussed, it doubles, right? Question number 2, if the rate of a reaction is 50 degrees Celsius, at 50 degrees Celsius is 2.6 into 10 to the power of minus 3 mole liter inverse second inverse, then what will be the rate of the reaction at 80 degrees Celsius? And you should remember, for every 10 degree rise, the rate will be doubling, right? So I have 50 degrees Celsius, 60 degree, 70 degree, 80 degree. So at 50 degree we have 2.6, right? At this one it will become double, so it will become 5.2. okay, then after this one it will double, 10.4, then after that it will become 20.8 into 10 to the power of minus 3, right? Now if I just arrange it, it will become 2.08 into 10 to the power of minus 2. So the correct answer here is option number A. Okay. The activation energy for the exothermic reaction A to B is 80 kilojoule. So if I have a graph like this, exothermic reactions will be like this, right? The energy of the product will be less than the energy of the reactant. Now what is the activation energy here? The activation energy will be 80 kilojoule, okay? And the heat of the reaction, means the delta H of the reaction, is how much? 200 kilojoule. The activation energy for the reaction B to A, means for this side, what is the activation energy? This is the total activation energy, 200 plus 80, that will be 280 kilojoule per mole. Option number C here. Moving to the next question, the activation energy for the forward reaction X to Y is 80 kilojoule. So we have C. Again you can see delta H is minus 20, means this is a exothermic reaction. So again the graph has to be drawn like this. The activation energy for the forward reaction, so this is X and this is Y. Forward reaction is X to Y. So for this one the activation energy value is how much? 80 kilojoule per mole. Okay, and the delta H for this is minus 20. This value is minus 20. Calculate the activation energy for the reverse reaction. Okay, so if you see, you will get how much we will get. This is 80 and this is 20. So negative doesn't matter, this gap is 20. Negative is because this is Y minus X, that is why we are getting negative. So 80 plus 20 will be 100. So that is why option number B here. Okay. Next, last question, again a similar question here. Energy profile of the reaction A plus BC gives you AB plus C is given in the figure. Which of the following statement is true? The threshold energy of the reaction is 100 kilojoule. This value is called as your threshold energy. So it is 100 kilojoule. Yes, it is true. Then the question is asking true only. EF means the energy of the forward reaction is 60 kilojoule while ER is 40 kilojoule per mole. They are asking you about the E stands for activation energy, right? So the activation energy for the forward reaction means this value. This value is 60, yes, and the activation energy for the reverse reaction, that is from this to this, 60 to 100, this value is 40, right? So that is correct statement. Yes, this is also correct. Next, delta H is 20 kilojoule per mole and the reaction is endothermic. So if you see, the energy of the product is more than the energy of the reactant. So yes, it is a endothermic reaction. And if you see 40 to 20, so this 40 to 60, this gap is also 20, right? So that is why that is true, and all of these are true. So the correct answer for this question will be option number D here. Okay. Next, we will move to the homework questions. So I have given you 3 questions here. Oh sorry, this time, yeah, 3 questions are there. So please try these questions and you have to comment your scores in the comment section. In round 1 how much you got, round 2 you got. So in the last video I haven't found any response, I don't know why. So but still, if you have studied, if you have seen this video, if you have liked this teaching, please put a thumbs up. So that was the end of today's class and I hope you have enjoyed it. Please put down the homework answers and the round 3 rounds solutions in the comment section. Put down your scores and I hope you have enjoyed the session. So if you comment down, I'll be definitely recognizing you in in the next session. So please do that, and all the best. Keep studying and keep smiling.